Okay, so last time we had this proposition, and it said if P is irreducible and aperiodic, and X is finite, then there, oh wait, yeah. Oh, sorry, this is the proposition that we were using to prove the theorem. Okay. Okay, what I actually want to be showing is this theorem that for any mu, any distribution mu on X, we have mu p to the I converging to pi, and here we were saying that this is a irreducible aperiodic Markov chain on the finite state space. This is like the initial distribution that we have for this, the x0, and then we're saying that as you run the Markov chain, this should converge to the stationary distribution. Okay. So what were we doing? We said, so we want to show that p to the I of xy converges to pi of y for all x and y. And so this amounts to showing that p to the I, which is some matrix, is converging entry-wise to this matrix capital Pi, where all of the rows, so all rows are pi, a little pi. Okay, and then we said, because of some proposition that we had before, that there exists R and some theta between 0 and 1, such that p to the R of xy is at least 1 minus theta pi of y for all x and y. And then we let q be this thing. It was 1 over theta p to the R minus 1 minus theta capital pi. And we said you can check by just writing things out that this is the transition matrix of some Markov chain, so all the rows add up to 1. Okay, so then what I want to say is that what we also had just by this definition, okay, I want to say we want to show this identity, p to the rk equals 1 minus theta to the k capital pi plus theta to the k q to the k. And the case k equals 1 just follows from this. And then for larger values of k, we're going to use induction. So use induction. And I want to note that, first of all, capital pi p to the r is the same as pi. Okay, well, why is this? Well, because little pi is stationary for this Markov chain. We know that like we have this identity, pi p equals pi, but then you can soup that up by taking this capital pi, which just has all of its rows being little pi, and then that ends up turning into, so this implies capital pi p equals capital pi, but then you can just iterate this and take any power of p here. So this also implies this. Then also q pi, I claim is pi. I forget. I think maybe I justify this. So the point is, this is pi. Or wait, sorry. Yeah, this is pi. Okay. Okay, and then we just had to do a computation. So we're going to say, let's prove this by induction. So if we assume that it's true for k, and we want to do the k plus 1, so p to the r times k plus 1 equals, well, okay, it's p to the rk times p to the r, which is the same as, okay, so let's plug in what we want here. So that's 1 minus theta to the k pi plus theta to the k q to the k times p to the r. Okay, let's rewrite this as 1 minus theta to the k capital pi. And okay, so here I'm distributing the p to the r in, but pi p to the r is the same as pi. So I can just write that as this. And then I can say this is plus theta to the k q to the k times p to the r. But what is p to the r? Well, that's just coming from the k equals 1 case here. So p to the r is actually the same as 1 minus, let me write it as 1 minus theta capital pi plus theta q. Okay, now we just play with this. So this should be 1 minus theta to the k capital pi plus, okay, what do we want to do here? Theta to the k minus theta to the k plus 1 coming from this. And then I want to have q to the, oh, okay, so I want to take q to the k times pi, but q to the k times pi is pi because I can also iterate this by putting a k there. So actually, so this q to the k pi is just pi, so this term becomes that. But then I'm left with this term where I'm going to get a theta to the k plus 1, q to the k plus 1. Okay, and then this is what we want, I think. Yes, because now I combine these, I get 1 minus theta to the k plus 1, capital pi, plus theta to the k plus 1, q to the k plus 1, and that's what we wanted. Okay, so now how does this let us finish? Okay, so in general, so this is like expressing p to the power of some multiple of r, but in general we can just say, okay, p to the rk plus j. If we take any integer, we can write it as, just use the division algorithm to write it as rk plus j. So this is going to be 1 minus theta to the k pi plus theta to the k q to the k p to the j. So all I did was I took this expression here. No, well, I took this expression here, and I multiplied by p to the j on the right. But if I take pi times p to the j, that actually just gives me pi. And then I have an extra p to the j here. So I have this. Okay, but then the point is that as
Wait, sorry, how are you getting rid of the p to the j on the left side and the right side?
So just this in this
Yeah.
step. Let me write out an extra step. So you want me to say this, right?
Yeah.
Plus theta to the k, q to the k, p to the j. Well, the point is that pi p. Oh, so I guess I wrote r here, but like literally just for any integer m, we have pi p to the m is pi.
Okay.
Right, so that's what I'm using here. So this is this. Okay, but now the point is, if k is growing, right, so you imagine taking this exponent to infinity, so the k is going to be growing if you're using the division algorithm to write your thing as some multiple of r plus j. Well, as k is growing, because theta, so theta is between 0 and 1, so this is shrinking, this theta to the k, but q to the k times p to the j is the, like, q is the transition matrix of a Markov chain, and p is the transition matrix of a Markov chain. And if you multiply transition matrices of Markov chains, you get a transition matrix of a Markov chain. So this whole thing is a transition matrix of a Markov chain, meaning that the entries are bounded between 0 and 1. So if you're taking some matrix with entries bounded between 0 and 1, but then times theta to the k, which is very small, then that's going to 0. So this is, and then the theta to the k is going to 0, so this whole thing is converging to capital pi. Okay. Is that good?
Could you quickly go over what Q is, like how you got that expression for Q?
Right. Well, yeah. I mean, I got the expression because I guess this is what works. Like I didn't come up with this proof. I don't know if I have a good reason why you would want this to be what you choose Q to be. Yeah. Let me think about it.
And like, are we assuming that Q to the K of pi is equal to pi? Like, if Q is a different Markov chain, and pi is like the same stationary distribution for P, or like the original like probability of going from state to state, like how does that also stay the same?
Wait, sorry.
Like, how does Q to the K of Q to the K times pi also equal to pi?
Oh, well, so this, I think we justified, so I did some brief computations last time to say that q pi equals pi. I think I did that, did I? Okay. And then you can just iterate that and say, okay, then q squared pi is pi and q cubed pi is pi.
Okay, and that's not true of like just a general Markov chain. That's specifically true because of the way that we define Q.
I think in this case it's actually just because it is the stationary distribution of a Markov chain. Here, I mean, I can do the computation again. It's pretty quick. I think it's because it's the stationary distribution of a Markov chain and because of the way that we define capital pi. So this was just q capital pi of some xy is just by matrix multiplication. This is the sum over z of q of xz pi of zy, and then q of xz. This is just the same as little pi of y because of the way that we define the matrix capital pi, just all the rows are little pi. But then this was, well, okay, the sum, you can factor this out of the sum, and then you're left with pi of y, but this sum becomes 1 because you're just saying it's the probability of going from state x to somewhere. So that's 1. And then this is like capital pi of xy, just because all of the rows are pi.
Okay.
Yeah, so it's not really using anything other than the fact that Q is the transition matrix of a Markov chain to get that this sum is 1. Yes?
Right after you wrote down this theorem, you wrote a lemma, but we didn't, like, here we proved the lemma as like a corollary, but is that, like, we didn't use the lemma anywhere, right?
I think we used, so the lemma was saying that if you have an irreducible aperiodic Markov chain, then there is some R. Yeah, I think it was used to construct this R such that this works. Yeah. Okay. All right, let's see. So I want to mention, or maybe for this class I'll discuss the problem of saying, okay, you have, well, what we've been doing here is saying we have a Markov chain, and we want to find its stationary distribution. But on the other hand, you might start with a stationary distribution, like maybe you have some interesting distribution on some set of objects, and you want to construct a Markov chain whose stationary distribution is that thing, is that distribution. And there are a lot of practical reasons why you might want to do this. This is basically the setting of Monte Carlo methods. So the point is that maybe you have some distribution on some objects and you want to be able to sample, like what does a random one of these objects look like if I sample from this distribution? Well, maybe that's a difficult problem to do computationally. So instead what you do is you set up a Markov chain that's easy to run, like on a computer, and then you just run it for like 10,000 steps. And because of this convergence theorem that we proved, you can say, well, if I run it long enough, then I can be kind of sure that the object that I'm going to get is sort of close to what I would have gotten if I had sampled according to this distribution. And it's an approximation because this is converging, but the hope is like, well, maybe it's converging fast enough that it's like a good approximation. And then later we can talk about mixing time, which is giving some kind of quantitative measure of like how long do you actually have to run the Markov chain. But for now, let's just look at how do we construct a Markov chain with some stationary distribution. Okay, so let's first consider, okay, so suppose that we have some psi, which is a symmetric transition matrix of a Markov chain. Or I'll just say symmetric Markov chain. Symmetric just meaning it's symmetric as a matrix, which in the phrasing of the Markov chain means that the probability of going from state x to state y is the same as the probability of going from state y to state x. Well, okay, in that case, then this is reversible with respect to the uniform distribution. Reversible with respect to the uniform distribution. And we saw that that means that the uniform distribution is actually the stationary distribution. Okay, so now what I want to do is modify this Markov chain to create some new Markov chain that has a different stationary distribution. So, okay, here's how we're going to do this modification. So suppose we're at state x, and I want to define this transition. Suppose we are at state x. choose a candidate from the distribution psi of x dot. So what I mean by that is basically pretend that you're going to do a transition in this psi Markov chain. So that gives you some place where you might want to move, but then you might decide to not actually do that, to not actually move there. And so you have some probability. Okay, maybe I should say choose a candidate y, and then say you'll have some probability a of xy, so accept with probability a of xy, and reject with probability 1 minus a of xy. So when you reject, you just stay at x. So I'm saying, okay, pick a new state where I might want to move, and I have some fixed probability that depends on x and y, and with this probability, I will move, I'll actually do the transition, and with probability 1 minus a of xy, I just stay still and don't move. So this gives us some new Markov chain, which is going to have some different stationary distribution. So now what I want to observe, okay, yeah, so let's, so observe that we have this new transition. Okay, so let's call P. Let's say P is now our new Markov chain with that's defined by this acceptance or rejectance rule. So then P of xy is going to be psi of xy a of xy if y does not equal x. And it's, well, whatever is needed, like it's the complementary thing if y equals x, just in order to make these sum up to 1. So that would be 1 minus sum over z not equal to x of psi of xz a of xz if y equals x. Okay, so let's say we have some probability distribution pi, and we want to choose the a's. Like by choosing the a's appropriately, we can try to make the stationary distribution of p to be whatever we want. So let's say we want it to be some little pi. So we have some goal distribution little pi, and we want to have that little pi of x, psi of xy, a of xy, equals pi of y, psi of yx, a of yx. Right, so this would just say that we have, that our Markov chain is reversible with respect to this this little pi, and then that would mean that little pi is our stationary distribution. Okay, so we've made a simplifying assumption that psi is a symmetric Markov chain, which means that actually psi of xy equals psi of yx. So actually we can cancel this and just say we just need pi of x, a of xy to be equal to pi of y, a of yx. Okay, so here's how we're going to choose this. Let's take a of xy to be the minimum of pi of y over pi of x and 1. Okay. And this should, well, okay, so if a of xy is pi of y over pi of x, then this works. And then, okay, what happens if pi of y is bigger than pi of x? In that case, where does this work? Yeah, so let's see, if pi of y is bigger than pi of x, then so this becomes pi of x, and then a of xy should be 1, and we want that to be pi of y, or sorry, yeah, then, okay, I see. A of yx is going to be pi of x over pi of y, because then pi of x is smaller than pi of y, so that's the minimum. So this becomes pi of y times pi of x over pi of y. So it works in the case when pi of y is bigger than pi of x, but then symmetrically it'll work if pi of x is bigger than pi of y. So this choice of a of xy satisfies this equation, meaning that if we use this choice of a of xy, then we get a Markov chain whose stationary distribution is the one that we wanted, which is this little pi. Okay, so maybe one thing to note is that when you, so I should give this a name. This is called, the metropolis chain for the distribution pi. Okay. And I guess, okay, one thing to note is that, well, if you're going to implement this, you'd like to have it converge quickly, and maybe in some cases, because of the way that you have to choose the a of xy, it actually slows down the mixing time, and that can be bad. So maybe in practice, there's some art to trying to maybe find a different Markov chain that's not this metropolis chain that'll converge more quickly, but this will at least do something. And these a of xy's only depend on the ratios, like pi of y divided by pi of x, which can sometimes be much simpler to compute than, say, the entire stationary distribution that you want to understand. So like, there are some situations where maybe one of the difficulties is trying to, like let's say you wanted to compute something, you wanted to choose something uniformly from some object. You have a set of combinatorial objects and you want to sample one uniformly. Well, in some cases this would rely on sort of knowing how many objects that you have. And maybe this is like not an easy question to answer. But here you kind of only need to know what's happening locally with these ratios between any two elements, which might be easier to implement. So there can be some advantages of this. Okay. So let me give one interesting setting. Okay, so what I want to do, okay, so let's say example. Okay, so let's let f be a real valued function on the vertex set x of a graph. So we have a graph. The state space of the Markov chain that we're going to consider is also the vertex set of this graph, and I have some real valued function on this set. Okay. So what you might want to do is try to optimize this function. Maybe in some kind of real world application, you want to find like a maximum for f. But maybe, maybe the domain, like maybe x is like very large, and so you can't just do an exhaustive search of all of the states to try to find what is the maximum. But instead, you can define, okay, here's an algorithm. So this is, so this is called a hill climb, and basically it's an algorithm where you say, okay, I start at some vertex, and if I see an adjacent vertex that has a bigger value of f, then I'll walk to that adjacent vertex, and then I do this again and again. I just keep walking to bigger vertices, and the hope is that maybe you arrive at a global maximum, but this might not actually happen because you could have some situation where, maybe you're walking along and you get to this peak, and so now you've reached a local maximum, but maybe it's not the global maximum. But then you're stuck there using this algorithm because the algorithm says walk to an adjacent vertex that has a bigger value, but if it's a local maximum, then you're not going to walk any further, and you're going to be stuck there, and you're not going to see the global maximum. So you can try to use randomness to try to get unstuck from this, this local maximum. So what you can do is say, okay, I think for simplicity, let's assume that the graph is regular. So assume, for simplicity, that the graph is regular, which just means that all of the vertices have the same degree. Okay, and then in that case, that means that a simple random walk on this graph has a symmetric, it's a symmetric Markov chain, right? Because if it's a regular graph and we do the simple random walk, then the probability of going from x to y is going to be the same as going from y to x, just because all the degrees are the same. Okay, so then we can do this. Let's fix some lambda greater than or equal to 1 and define pi lambda of x. So x will be one of the vertices. This will be lambda to the power of f of x divided by some normalization z of x. We're here, okay, so z is just going to be the sum over all states y of lambda to the f of y. Okay, so with this normalization, this becomes a probability, yes?
I think you mean z of lambda, not z of
Oh,
x.
yes, I do, thank you. Yep, yeah. And here's z of lambda, yep. So z of lambda is just this normalization factor that makes sure that this is a probability distribution. Okay, so one of the issues with this is that in practice it might be hard to compute this distribution because it might be hard to compute this z of lambda. Because computing the z of lambda requires summing over all of the vertices of your graph, and maybe your graph is ginormous. But instead, if you run this metropolis chain, then it can be easier, and you don't have to actually compute this because, again, like you only have to care about these local values of these ratios. Okay. So, okay, so we're going to do the metropolis chain. Okay, wait. To try to approximate this distribution. And the point is that if lambda is big, yeah, so the point is that this is going to give a lot of preference to the states where f is large, right? And so we can try to approximate this using the metropolis chain. So I'll say if f of y is less than f of x, then the metropolis chain will accept the transition going from x to y with probability lambda to the power of negative f of x minus f of y. Okay, that's just because if f of y is less than f of x, then we use this ratio, and we get that, well, just the ratio given the formula that I wrote down for the pi y of x, it's this thing. And so then the point is, well, so as lambda goes to infinity, this more closely approximates the deterministic hill climb. Right, because if lambda is very big and f of y is less than f of x, then this is going to be some giant number to a negative power, which is very small. So it's going to say that, like, almost all the time you're not, accepts, am I getting something backward? So you accept with this probability if lambda is big. Oh, wait, yeah. something off? Oh, I see. Okay, yeah. The point is that, okay, if you're at x and you're going to y, you don't want to accept in the hill climb, right? Yeah, so that's why, yeah, if lambda is very big, then this acceptance probability of going from the local maximum, to like leaving the local maximum becomes very small, so it's very close to the hill climb. But if you can try to balance your lambda and maybe choose it not too big but not too small, then you can try to optimize this to get some algorithm that will try to find a local maximum, or a global maximum. So, okay, let me define x star to just be the set of places where the actual global maximum is occurring. And then the point is that if you take the limit as lambda goes to infinity of pi lambda of x, this is equal to, well, okay, it's going to be the limit as lambda goes to infinity of lambda to the f of x over, let me give a name to this. Let's say, let f star be this maximum. So this is going to be over lambda to the f star divided by the size of x star plus the sum over x in the vertex set minus x star of lambda to the f of x over lambda to the f star. Okay, so this is just because, well, okay. We're taking lambda to the f of x divided by like z of lambda, and we write out the definition of z of lambda, but then let's divide the top and the bottom by lambda to the f star. Well, if you divide the top by lambda to the f star, you get this. If you divide the bottom by lambda to the f star, everything in x star becomes 1, so it contributes a factor of 1, which is why you get the size of that set. And then all these others, you get this quotient. And then the point is that as lambda is going to infinity, if f of x is smaller than f star, then this is going to go to 0. And if, and also these are also going to go to 0. Oh wait, sorry, I shouldn't have an x here. Let's say z. So if you take the limit, basically this becomes like the indicator function of whether or not x is one of the places where f is maximized, divided by the size of x star. Again, because these terms are going to go to 0, and this will go to 0 if f of x is less than f star, and it will go to 1 if f of x equals f star. And so this, in the limit, this distribution is the uniform distribution concentrated on the values that we care about, which are the vertices where this f is actually maximized. So the point is that if you run the Markov chain, then you should be converging to sort of what you want. Like you'll get a uniform sample from the actual global maxima. Now, again, there's a trade-off here because you want lambda to be very big so that this, like, because we're taking a limit as lambda goes to infinity, so we want lambda to be very big so that this is a good approximation of this uniform distribution on x star. But if lambda is very big, then you have a higher chance of getting stuck for a long time at some local maximum, because you're approximating the deterministic hill climb. So maybe you want to not choose it to be too big. Yeah.
Can you just recap how you got that last line, the limit?
This, yeah. So I'm just saying, let's do two cases. Let's say first that f of x is less than f star. In that case, this is going to 0, because that's going to 0. And then, well, in any case, actually, this is going to 0, right? Because these are the states z where f of z is less than f star. That's what it means to not be an x star. So no matter what x is, this is going to 0. So really, this should be going to the limit of lambda to the f of x over lambda to the f star divided by the size of x star. And then the point is that if f of x is less than f star, this is going to 0, which is what I mean by this. And if f of x equals x star, which is the same as saying x is in, or sorry, if f of x equals f star, then little x is in capital X star, and then this is going to 1. Does that make sense?
Kind of. I will look at that.
Yeah, so by this I just mean, right, so this is just 0 if f of x is less than f star, because that's exactly what it means for little x to not be in x star. And I'm saying this is 1 if f of x equals f star. Okay, there was another question, I think, maybe not. Yes.
Yeah. So basically you pick lambda, then you run the algorithm, and
Yeah.
and like just hope that you'll get there.
Yeah. I mean, I've never personally used this in practice. I'm just going off of the book. My guess is that, you pick some lambda, and maybe there's some art in terms of guessing what you want it to actually be. Yeah.
Wait, so why would that last? I'm confused by like, so we got that last time the end row limit lambda to infinity of pi y x equals like the indicator over that set. Like why? It seems to me like that's like, well, what's wrong with that? Like why would that not concentrate on like the maximum value? Like
I think
I didn't understand your point about like you don't want to pick lambda too large.
Oh, yeah, maybe I'm wrong about that. I guess what my thought was that if lambda is very big, then you could get into a situation where you're stuck at some local maximum, and maybe you get stuck there for a long time. So maybe it takes a while to actually converge, like the mixing time might be large.
Oh, but it will converge.
It will, yeah, the distribution is converging. So if you just care about having the distribution, then you want to take lambda big. But you want to avoid a situation where you get stuck for a really long time at some local maximum that's not the global maximum. Okay. So I also want to discuss what's called Glauber dynamics. Which is kind of very general, but we'll give some examples. So, so the state space that we consider will be of the form S to the V, okay, where V is the vertex set of some graph, and S is some finite set. Okay. So you can visualize this by saying you have your graph, you can visualize the graph, and then imagine that you've labeled each vertex with an element of this set, capital S. And here, S to the V is functions from V to the set S. Okay, so then say we're given some probability distribution pi on the state space. We're going to get some kind of Markov chain whose stationary distribution is pi. And I guess sometimes this is called the Gibbs sampler. So okay, I'll just say we will construct a Markov chain with some prescribed stationary distribution and this is called the Gibbs sampler. Okay, let me do an example actually to start. So we're going to consider colorings of our graph. So let's say we have some, so let's say S is just a set of numbers from 1 to Q. Q is just some positive integer. And these are going to be the set of colors that we have that we can use to color the vertices of our graph. And proper Q coloring of the graph is, well, an assignment of a color, and the colors are the numbers from 1 to Q, so that adjacent vertices have different colors. Okay, so what we want to do is, oh wait, oh, maybe I should have said the state space will be a subset of something of this form. Will be a subset of a set of the form S to the V. So maybe we don't want all of the functions from V to the set S. Maybe we just want some particular ones. So in this case, we're not looking at all ways of coloring the vertices. We're only looking at the proper ways of coloring the vertices. So we don't count the ones where, like, maybe you have two adjacent vertices of the same color somewhere.
Sorry, is the set S representing the colors here?
Yes. Yeah. Okay, so let's say we're given a proper Q coloring And yeah, so maybe X is our proper Q coloring, so it's a state of well, we're going to construct a Markov chain, and this will be a state, and a vertex V in V. And then we'll say a color J is allowable at V if J is different from all of the colors assigned to the neighbors of V. J is different from all colors, I'll just say adjacent to V in the configuration X. Okay. And so what it means to be allowable is like if I take the vertex V and I change its color to J, then that will still be a proper color. Okay, so then what we're going to do is, so here I'm going to construct a Markov chain by telling you how to do a transition. So for the transition, we're going to select some vertex in our graph uniformly at random. Yeah. So select a vertex V at random. And then select a color J randomly from the ones that are allowable. From those allowable at V in this, in X. And then just recolor it to J. Okay, so I'm just picking a random vertex, and then I say, okay, what are all the possible colors that I could change my vertex to be so that I still have a proper coloring? And then I just pick one randomly, and I change it to that color. Okay, oh, maybe I should say, I want to select this, okay, uniformly at random. Yeah, so if I do this uniformly at random, and I color this uniformly at random, then this will convert, the stationary distribution will be the uniform distribution on colorings. Yeah, so okay, the reason for this is just, okay, yeah, so if X and Y are two colorings, I want to check that this Markov chain I've just defined is reversible with respect to the uniform distribution. And the point is that if I take any two colorings, then the probability, okay, so let's say X and Y are two colorings that agree everywhere except one vertex. Well, then the probability of going from X to Y is just or maybe I should say the set of allowable colors at that vertex in X is the same as the set of allowable colors at that vertex in Y, right? Because they agree at all of the neighbors of that vertex. Let's call this vertex V. So the allowable colors at V in X are the same as the allowable colors at V in Y, which means that the probability of going from x to y is, well, first I have to choose v, which is done uniformly at random. And then, oh, maybe maybe I actually didn't need this to be uniform. And in fact, maybe I didn't need this to be uniform either. Yeah, right. I'm just choosing it randomly, but the point is that, yeah, when I go from x to y, I'm choosing something randomly among those colors that are allowable, but those are the same colors if I was going from y to x. So the probability of going from x to y equals the probability of going from y to x. But then, okay, if you have two colorings that don't agree, like in all but one vertex, well then the probability of going from x to y is 0. So, and the probability of going from y to x is 0. So again, these are equal. So this is actually symmetric. So it has a uniform stationary distribution. Okay, so this is the Glauber dynamics for proper Q colorings. Yeah, so this was one example. Yes?
It should be clear, so like a point or a state in this set is a coloring. We're no longer moving between vertices, right?
Right, yes. Yeah, so a state of our Markov chain is now a coloring of the graph. And in our Markov chain, we're moving from one coloring to another coloring. Yeah. Okay, let me give one other example, which is the hardcore model. Okay, so hardcore model. So here I'm going to take the set S to just be 0 and 1. And you can think of 1 as representing a particle and think of 0 as representing no particle. And so a configuration, like an element of S to the V, you can visualize as just a configuration of particles sitting on some of the vertices, not all of them. And we're interested in a hardcore configuration. So, okay, a hardcore configuration is I'll define it as a function in S to the V such that no adjacent vertices are both assigned 1. Okay, so you could think of it as saying, like, you have a bunch of particles sitting on some of the vertices of your graph, but the particles kind of repel in some way, and you're not allowed to have two particles sitting next to each other. This is also just called an independent set. So maybe I'll also say an independent set of the graph. Just saying, if you look at the vertices of the graph that are assigned 1, then that's a set of vertices where no two of them are adjacent. That's called an independent set. Okay, so now what I want to do is define a Markov chain. So let's do the following. So define a Markov chain. So first, choose a vertex V uniformly at random. And then, if any neighbor of V is occupied by a particle, meaning that it's assigned the value 1 in this function, then, well, that means that V was already unoccupied, and we're just going to keep it unoccupied. V stays, or I'll call it vacant. But if so if no neighbor of V is occupied, then V stays, well, I'll say V becomes occupied with probability 1/2. And becomes vacant with probability 1/2. Okay, so you just pick a vertex uniformly at random, and you say, well, am I allowed to put a particle on this vertex? And if you're not, because it has an adjacent vertex that's already occupied, then you just do nothing, you just keep it vacant. But if it has no neighboring vertices that are occupied, well, it could be the case that the vertex you chose is occupied and none of its neighbors are occupied. Or it could be the case that it's vacant and all of its neighbors are also vacant. But in either case, it doesn't matter. You just say, I'm going to flip a coin, and if it comes up heads, I'll like either put or keep a particle there, and with probability 1/2, if it comes up tails, then I'll make it vacant. Okay, and so this also will give you a uniform distribution, like the stationary distribution will be uniform on the set of these hardcore configurations, and maybe I won't go into that. That's very similar to in the case of the Q colorings. Okay, let me maybe just mention the more general definition. Maybe we won't do much with the more general definition of the Glauber dynamics. But like the Q coloring thing here and the hardcore model were special cases of a more general thing that people study. So in general, you take the state space of your Markov chain to be some maybe interesting subset of S to the V, where V is the vertex set of your graph and S is some set, some finite set. Okay, and then pi is going to be some stationary distribution. So pi is some distribution I'll say supported on X, or you can just think it's a distribution on X. So here's how we want to define this Markov chain, which is going to be the Glauber dynamics. So we're going to choose a vertex uniformly at random. Okay, so choose V in V uniformly at random. And now, okay, we choose the new state using pi. So new state I'll just say according to pi, but conditioned on only considering the set of states, so the set of states. Okay, so let's say we're at, so we are at x. X is some state. We choose our vertex uniformly at random, and then we say among the possible states that we could change to by only changing the vertex little v, so we're only allowed to choose this, but among those states that we could move into, we choose one according to the distribution pi. Okay, set of states that agree with x everywhere except possibly at x or at v. Yeah, and so, okay, this is the Glauber dynamics, and the point is this is going to give you some Markov chain, and it turns out that this will converge to this distribution pi that we're interested in. And maybe in some cases this is easier to handle than like the full distribution pi, because you only have to care about things locally if you want to run this Markov chain. Like at each step you're only changing one single vertex, so that might be easier to handle than looking at like the whole graph. Okay, so I think maybe I'll stop there for today. Yes?
So that example with the cube coloring and the hardcore model are two examples of Glauber dynamics.
Right, yeah.
Got it, perfect, thank you.
Yeah, so this is like a very general setup, but I think these are like interesting examples. Yes?
Can you just explain one more time what like this set of states that agree with x everywhere except possibly b?
Yeah, I just mean that I've assigned an element of capital S to every vertex. And so I have some state little x, which is some assignment of elements of S to the vertices. And now I have this vertex little v, and I just say, look at all of the assignments that are the same on all of the other vertices, except maybe at v.
And so there